that is interchangeable with this. My claim is that this is true because on the left-hand side, if you multiply it out, what you get is cosine theta, cosine beta, minus sine theta, sine beta, but that's exactly the cosine of theta plus beta. And for the imaginary part, you get sine theta times cosine beta plus the cosine of beta times the sine of theta. And that's sine of theta plus beta, which is the adding angles formula for sine and for cosine. And if you took my calculus 1, you'd have proved that those things are true from like trigonometry. But that's the proof. It rests on actual coordinate trigonometry arguments that are based on the Pythagorean theorem and perhaps the law of cosines. Or did I use these to prove the law of cosines? I can't remember. But it's just trigonometry, all right? So, but my larger point to you is that this imaginary exponential notation, it like naturally folds the deeper truths of trigonometry into what appears to just be laws of exponents. It's an incredibly slick notation for the adding angles formulas for sine and cosine. It has the full power of the adding angles formulas for sine and cosine. It's stupidly useful. For example, if we take e to the I theta, oh no, I must not do that. If this is a rabbit, if I chase it, we'll lose 10 minutes, and I want to tell you more interesting things in those 10 minutes. So I will not do that. All right, so I need to define for you guys. I just threw out theta as the standard angle here, but we have notation to be more systematic about this, and this is important. All right, and it's a little bit fussy, but here's the definition. Let z be a complex number with z not equal to 0. Then the so-called principal argument, I may misspell that, who knows, principal argument of z is theta naught an element of minus pi to pi included, all right, for which z is equal to the modulus of z times e to the I theta naught. All right. We denote arg z, arg theta naught. Theta naught does not have a fixed meaning, but capital arg z does. This is a privileged fixed notation in this course for the principal argument. All right. And so, more generally speaking, I also define in a similar way arg sub alpha plus of z to be equal to little arg z. I'll explain what little arg z is in just a second. Little arg z intersect with alpha minus 2 pi comma alpha included, and then arg alpha without the plus z equal to little arg z intersect with alpha included comma 2 pi plus alpha excluded. Now here little arg of z is equal to big arg of z plus 2 pi I times the integers. These are all definitions.
Is that an intersection?
Intersection. So there we go.
What is arg? Is that the principal argument?
Mm-hmm.
Like, what does it stand for? Arg?
Arg.
What does it mean?
Arg. It's the principal argument.
Okay. Got it.
What's your name?
Rachel?
Why is your name that?
I don't know.
I mean, there could be a reason, but it's just the name of it. I mean,
Okay.
it is, what does it mean? I think of it as this, it's the standard angle of z, which resides in this choice of angles.
Okay.
So each one of these arguments, to answer your question in a less annoying way, each one of these arguments is just a choice of angle.
Okay.
It's a specific choice of angle function, an unambiguous choice of angle function, right? And as long as you throw out alpha, it's a continuous assignment of angle. There's a jump at the alpha because that's where geometrically you're jumping from that angle to like back to this again. So like if you use the standard argument, if we look at what's called the slit complex plane, we have to throw out this here. This is C minus. C minus is the complex plane without the negative real axis, all right? And so there is a continuous assignment of angle for every point in the slit complex plane, ranging from minus pi not included to pi included. Now, if you actually include the pi, it's no longer continuous because you've got to jump from minus pi to pi as you approach this way versus that way. All right, we'll talk more about this, but I'm just throwing it out there. So this is argument. So the principal argument is single function. This is not a function. This is multiply valued. See, argz is a set of values. For example, the argument of 1 is equal to 0 plus 2 pi iz. To be more explicit, it's the set 2 pi I k such that k is an integer. The underlying thing that we're struggling here with is that we lose the one-to-one property for the imaginary exponential. All right? We lose it. Because like the fundamental issue is this. Here's the problem. It's not a problem. I mean, it is a problem, but it's also beautiful and neat. So e to the I theta equals e to the I beta implies what? It does not. It implies that theta minus beta is an element of 2 pi iz. Because this means that like cosine of theta is equal to cosine of beta, and it means that sine of theta is equal to the sine of beta, right? Theta and beta don't have to be equal to make those two things equal. You can add 2 pi multiples and still get equality, right? I can have theta as pi, I can have beta as 3 pi, or 5 pi, or 7 pi, or 9, we could be here all day. So we lose the one-to-one property, but the departure from one-to-oneness is not too bad. It's just this, and that's part of what this argument is invented to deal with. Like everything, if you think about it, everything in the argument of z, if you feed anything in the argument of z, let me just say it this way. If we had theta 1 and theta 2 in a particular like little arg, then you can easily check that e to the I theta 1 is equal to e to the I theta 2. Because what they differ by is at most a 2 pi multiple of I. And it's an identity of the imaginary exponential. You can easily check this. If we have e to the I theta plus like 2 pi k, that's equal to e to the I theta. I mean, this is like basic trigonometry, that if we add 2 pi integer multiple 2 pi to the argument, the input of sine and cosine, we get back the same sine and cosine without the 2 pi multiple, right? That's still true for the imaginary exponential because it's just built by a combination of sine plus cosine in this way. So that's basic trigonometry, and the impact of it is this, among other things. Now, I'm sorry, if I'm not being super clear, read the notes. They're probably a little bit better on this overall. And I also have quotes from Gauss and stuff, which I think are good. What I wanted to show you today was how we can use this imaginary exponential to calculate like fifth roots of a complex number. But that's going to have to wait for next time, and that's fine. We don't have to hurry. So if I get too far behind, I'll make a video, you know. It's okay. But I did want to show you something today before we leave, because this kind of belongs in this lecture. And so the question that remains that I haven't really delved into is, what are complex numbers? See, I just gave you this like kind of formal definition, but I didn't really tell you what they were as objects. And the answer is, well, there's different ways to look at this, but one way to look at it is, and I think this is the most mature way, is that the complex numbers are a formal system that satisfies the rules that we've looked at today. The distributive, the commutative, the fact that there's an imaginary unit whose square is minus the multiplicative identity. These things really make the complex numbers what they are. But there are at least 3 ways to construct the complex numbers from other mathematics. The one way is just to take the plane and define a special multiplication on it. This is what I call the Gauss model. And really, what we've done is that. We just have like a slightly, come on. Let's see here. We have a slightly, what's the word? We have a slightly nicer notation, but you see, if you add the component, that's how we defined addition. And this is exactly how we define multiplication. We just, instead of writing AC minus BD, comma AD plus BC, we put it plus I. But this is really what we did today in a like less nice notation. And you can suffer through that and prove all of these things, like this times this is that. We did that in the other notation today. Or this times this is -1. You can prove that. All this stuff, right? That's one way you could do complex numbers. And the double scrolling, it got me. Oh man, we really scrolled up. We're like way in the future now. Sorry guys, I will. Here we go. All right, so the other way is you could look at 2 by 2 matrices of the form AB minus BA. If you look at these matrices and you multiply them, the identity matrix behaves like the number 1, and the matrix 0, 1, -1, 0, it squares under matrix multiplication to minus the identity matrix. So that's like the number I. And so this is another way. You could build complex numbers as 2 by 2 matrices. We had a professor who used to take that as the definition of complex numbers because he likes matrices. Right? Another way is with abstract algebra. You could build it as the quotient ring of real polynomials. You just mod by the ideal generated by x squared plus 1. In this wild world, x squared plus 1 is 0, which means that x squared is equal to -1, which means that x times x is -1, which means that x behaves like the imaginary unit. These are 3 different ways you can build the complex number systems. Now, which one is it? For the sake of specificity in here, we're going to use the Gauss model. We're going to think the complex numbers is literally the point set of the plane with this special multiplication, and that's how we're going to go. But there are other ways you could build it. It's really a matter of taste. So anyway, I will shut up. Thanks, guys.